Okay, so we're going to be talking about sweepline. Sweepline is used in various applications. So sometimes we use it for geometry problems, and other times we use it when there's some kind of process that we like to simulate, and the order in which we do it sort of gives us more information about what's going on. All right, so let's just get right into it. Why is my sorry? No, what? Can you guys see my sidebar here? Can I make this go away? Okay, I guess that's not so important.
It's fine. It's small.
Yeah. Okay. Anyway, so yeah. So this is a very classic leak code problem. Meeting rooms. So the idea is that you have like n meetings that start at like SI and at EI, and so if you have multiple meetings going on at the same time, you would need like at least like more than one room. Like you need one room for each of them. So given the start and end times, calculate the maximum number of rooms you would need at the same time. So if you've seen this problem before, it's fine to just say what's going on. But this is basically a very nice way to introduce where sweepline starts to become helpful. So any thoughts of how we can do this? So like, given the constraint, you need pretty much linear, or like linear with a very quiet log factor.
Wait, so you can like pre-process the your start and end times? So those are gonna be like, you can probably process them in like, yeah. So all your starts will come before your ends, and then you're basically gonna like iterate through that. So you're gonna iterate through the sorted list, and then like you can have a plus one for a start, and then for ending you can like basically like take away one.
Yeah,
and then
exactly.
You're gonna have a running sum, like a max.
Yes. Yes.
Answer.
Yeah, that's basically the idea. So we can simulate the meetings. So this is a process that we can like actually pretend, oh, the meetings are actually happening. So one thing to not do by accident is like loop through a time variable, because like maybe like SI and EI are like 10 to the 18, and then now you can't loop through all the time. So instead, you would do what Jason said. You would sort by, so you create time sorted events. So the events either are starts or ends of the meeting. And if you have a meeting starting, you just add +1 to a counter, and if it's ending, you add -1 to a counter. And yeah, you just see what is the maximum value the counter reaches, and that's your answer. So yeah, so when we're doing sweepline, one thing that's helpful to do is have an enum. So we only started doing this recently, but it's actually very helpful. So one thing that's important is which event do we want to process first in the event of a tie? So let's say a meeting is ending at a time and a meeting is also starting at the same time. So like we didn't specify in the problem description, like it doesn't say what happens. But in this case, what would happen is that if a meeting ends and then another one starts, it's okay if both meetings use the same room. So in that case, it's okay if, or rather, what you should do is you should process the end of a meeting before the start. Because if you did it the other way around, you would increment for the start and then decrement for the end, and you would get a maximum 1 higher than what you just had. So so when you do an enum in C++ like this, end is like assigned a value of 0, and start is assigned a value of 1. But that's not so important. It's more like you can just sort of compare these two values. Okay, so now we're looping over all the n events. We're getting the start and end time, and we keep our vector of pairs. So what's going on is that we have the time, and then we have the event type. So we're sorting by time first, and then by event type. So if the time ties, then of course we're going to be sorting by type. So yeah, then we sort the vector. This is faster than using a set, so it's a little bit better to use a vector and then sort it. Although it might be like you might prefer to use a set, and usually that's okay. And then yeah, we just do what Jason said. So you keep a current count and you keep the maximum that the count has reached, and you just flip over the events and do precisely that, and you're done. Okay. Any questions on this? Nope. Okay, cool. All right. So now we have the circular variant of meeting rooms. So I don't think I've seen this problem anywhere, but it's like a nice way to sort of extend to sort of the geometric stuff that comes later. So now what happens is that meetings run at the same time every day. So like if I have a meeting that starts at SI and ends at EI, then that happens every single day. And it's also possible that EI is less than SI. And so in that case, the meeting would start at SI, run past midnight, and end on the next day at time EI, and also continue to do so every single day. So now it's slightly different. And so what would you do sort of to account for this variant and now count the maximum number of concurrent meetings? So sort of the tricky thing is that like if we try to do the same thing as before, the problem we run into is that some meetings are already going on um, when we begin the day. So like if we try the old technique, then we might run into an end event and try to do a -1. But that meeting hasn't started yet, so we might even get a negative number. So the question is, how can we account for these weird meetings that go past midnight? So you can treat them separately. So it wouldn't be too hard to say if EI is less than SI, increment the count before you start. And I think that would work. But it's kind of messy, and if the problem changes, then like it can become really hard to see what's going on. So there's an idea. So oh what? Okay. I guess the sidebar's gone. Okay, yeah. So Yeah, you kind of need to know how many meetings are going on at the start. So the idea is you can loop through it twice. So before you start processing stuff and like updating your answer, just loop through it once to see what is going on at the beginning. And we can also to not so when we do the first loop to figure out what's already on at the beginning, we can keep a set of the indexes that are currently on. So now if we remove from a set, then we're not going to have like a -1 issue. It's just not going to do anything. So here's what the code looks like. So this time, I have type as an enum again, but my event is now a class. And so the reason for this is because we kind of want to, so we're sorting the events, right? And we kind of want to, so one thing you could do instead of a class here is use like a pair of an LL and a pair of LL and LL, but that gets kind of messy to work with, and it's actually just a lot easier to say like e.tim or e.t or whatever. So it's just a little bit nicer to do this. So tuples also are by default sorted like in order, like you would expect it to be, but so is this. So this is fine. And again, type is an enum, so end is 0 and start is 1. Okay. So so one thing you have to do is for the constructor for ev, you can't do like anonymous bracket initialization. You have to type ev here. So it's like another 2 characters, but it's not a big deal. So yeah, push that back, sort. Okay, so yeah, we do this twice. So this is a special case where it's okay to just literally do this twice, but sometimes you want to do the processing of on or not first, and then separately do the actual answer calculation in a different loop. So anyways, so here we have this set LL of things that are currently on. So if we see an event that's a start, so T is the type, then insert it. Otherwise, erase it, because then it's of type end. And then we keep running max over the amount of things that we have currently on. So it's okay to do this twice, because like we'll never have a -1 or anything. And even if we did, like the max doesn't matter. Like maxing over that doesn't matter. But yeah, it's not always the case that you can just do it the exact same loop twice. Yeah. Okay. Does this make sense? Cool. Okay. All right. Yeah. So the idea with general sweep line is like you're processing events in some order, and you're usually going to have like at least 2 types, which are start and end respectively. And a lot of times you'll also see like this kind of onset. So you have some things which are active, and of course, like a start event corresponds to adding to this, and an end event corresponds to removing this. And usually, what you get from sweep line is reducing a linear factor to a log factor. Of course, the log factor is induced by sorting. Okay. All right. This is I think this is a problem that I've seen either in not GNYR, I think, but I've seen in some of the ICPC practices I did a while ago. This and some other like kind of messy variants. And it was back when I was using Java, so I was using like the really horrible tree sets. But yeah, that's in the past. no more tree sets. But yeah, okay. So you have n axis aligned lines. So basically, lines are not of 0 length. They are either horizontal or vertical. They start and end at integer points, and no two lines like overlap each other. Like they intersect at only a finite number of locations. So, and also if they intersect, they never touch at like, so if 2 lines intersect, it's never gonna happen like this. It'll always happen somehow like this. Okay, so basically you're told the lines are very well behaved. So now, given all these magical constraints, calculate the number of times that intersections occur. When you're given that n is 1e5, so like one thing that might be tempting to do is like, oh, maybe somehow I can just like calculate all the intersections, like just loop over all of them. But unfortunately, this doesn't work because what if we had oh no, okay, well this is fine. What if we had half of our lines going like this, and then half of our lines going like this? So in this case, you would have like n squared over 4 intersections, I think, if I'm doing multiplication correctly. And obviously n squared means you can't loop over every single intersection point. So that's not good enough. So you have to somehow, so like sort of some information you get out of this time constraint is you have to be able to calculate multiple intersection points in one go somehow.
So like, because they're like I said, I'm trying to say like you only care about one of the, like, let's say you set your orientation, and then basically like how have you had it before, and then you really only care for one of the coordinate planes, I guess, because you can really essentially stack the horizontal lines on top of each other, and basically we have like the same thing as meeting rooms again. Is you have you can think of this, you can just go through the for loop of the vertical lines, but then you stack the horizontal lines on top of each other.
I'm not quite sure what you mean by stack. So like, okay, let's think about the framework of sweep line, right?
Yeah.
So we want to phrase this in terms of events somehow, how we're sorting.
Uh-huh.
So what kind of events would we have, and what would we do to process the events? So it's a good first step to sort of think of the horizontal lines and vertical lines somewhat separately, because we would treat them very differently when we're processing them.
Yeah, it really doesn't matter which one you pick, but like one of them will have to be like one of the, like, I don't know what your terminology would be, but like one you will like pre-process one of the lines, and then the vertical other ones you will have to like run them in your second for loop.
So let's just draw some pictures. I don't know, maybe something like this. Okay.
Yeah.
So one idea is like, or rather, the only idea I can think of is so we want to sweep through it in this direction somehow.
Mhm.
So if we, just by saying this, you kind of naturally have the idea that there's only a few x coordinates that are actually interesting. And namely, those x coordinates are when a point starts, when a point ends, or sorry, when a horizontal line ends, and when we see vertical lines. Does that make sense?
Yeah.
Yeah. So we only have sort of 3 types of events, and now I can actually formally say, so like, this is a start event, this is a start event, this is a vertical line event, and so on. So another thing that we want to recall from sweep line is that we want to maintain an active set of elements. So also the natural way of thinking about this is that this line becomes on when we process it and off when we're done with it. So really, there's only one thing that we can do when we see a vertical line, we know that some number of horizontal lines are on. So what can we do to calculate the number of intersections based on that?
Just add it, right? Just add the number of ons you have.
So unfortunately not, because my picture is very misleading.
Are vertical lines, do they go on forever, or are they like?
No, so they have start and end points.
I see.
So I might have something like this.
Gotcha.
So this is actually kind of tricky. But I'll let you think about this for a minute. Raja is suggesting sort the horizontal lines by vertical position. So yeah, so how would you actually figure out? So yeah, let's say we sort the ones that are active, right? Maybe we put it in a set or like maintain some sort of structure that's sorted. How will this help us figure out how many things that this line intersects? So one thing that might help is if I actually label this as a, like in the vertical sense, and B. So actually this is kind of misleading because, so you might be tempted to think like, oh, well, if I maintained a sorted vector, then I can do a binary search for where I would insert A and B respectively. And the elements in between would be how many things I'm intersecting. But unfortunately, you can't maintain a sorted vector because when you want to remove from it, as we will do here, you just can't do it in time. So there's two options. So I'll just show. Right. Yeah, I'll just show. So you could do a seg tree. And that means that you can put a 1 on the Y position where you have a horizontal line active. And then in the seg tree in log n, you can take the sum over a range. And then that's good enough. So you would take the sum over basically booleans that represent a horizontal line being active on those spots. But this is a little bit annoying to write because you have some kind of bloat that's associated. So one problem is, let's say that like your y coordinates are huge, like maybe they're like 10 to the 18, which is fine in terms of processing because you only have n of them. But as a result, you would have to rank reduce the y coordinates. So you would have to say like, oh, this is like y coordinate 0, this is y coordinate 1, y2, y3. But you would also have to account for these spots too. So you could do a rank reduction based on just which y coordinate it is. And then the order remains the same. But yeah, that's kind of bloat that we don't want to deal with. So you can instead use ordered sets, which come from the PBDS, policy-based data structures. So the way to be able to use PBDS is you add these 3 lines to your code. So I think there's like, it's not always easy to include this stuff. The details are super hazy to me, but like, you might have to look at certain code forces blogs to ensure that you can use this correctly. But anyways, if you submit the code, it will work like when on like the online judge. So even if it didn't work locally, I guess you could submit it. But yeah, so the point of an ordered set is that it allows you to find the rank of an item in log. Joe, please correct me on this. Is it log n or log squared n?
I think it's log.
It's log. Okay, great. Yeah. But I think O sets are kind of slow though, right?
I think so. I mean, I think compared to sets, they're okay. Like just regular sets.
Yeah, but sets are also horrible.
Yeah, but I mean, I don't know. Usually fine.
Okay, sure. Yeah. Yeah. So with an ordered set, I can find the rank of an item, and I can also delete in log n time. So that means I can do the binary search trick, except it's not actually a binary search. And I can also delete things quickly. So now I'm good. Now I can figure out, okay, well, from A to B, how many items are there in between me? Yeah, so let's look at what that code looks like. So I have a type def for OSET. which is like how I write ordered sets. So if you Google goodcode.cpp, this is a Keith's. I think, does he have it in here? Oh no, he doesn't. Okay. But I think if you do this, ordered set, if you go here, they kind of explain how you can use ordered set. Hello? Okay, whatever. So you can replace the type of what you want in here. And then the rest of it is the same. And then you just type def oset as this, so you don't need to have this really bulky type definition. And yeah, so basically the main things you can use are find by order. So if you want the kth item, you can find it quickly. And you can also find order of key. So if you want to find out where something, like what position something would go in, you can use this. Okay, so let's go back to the code. All right, so again, we're using an enum. So now we have 3 types. So start, vert, and then end. So actually, it doesn't matter what order I do this in because of the constraint that lines never intersect at their endpoints. But if they did, then you would want to process the end of a line last, the end of a horizontal line last, because, so let's say like 2 horizontal lines are touching at a point, then that means that I want to end the left line for, well, let me just draw a picture so it's more clear. So yeah, let's say we have just only 2 horizontal lines and they touch at exactly this point. So I would want to start this line before I end this line. And the reason for that is so that when I start processing the start of this line is still active. So I count the intersection point, because if I didn't do that, it wouldn't work. And similarly, I want to process the vertical line before the end of a line, because it's important that I catch the vertical line intersecting this before I terminate this line. Similarly, so if I have a vertical line and then a start, then I want to do the start first and then the vertical line, so I catch this. So actually, this is the correct order in general: start, vertical, end. But it doesn't matter in this version. So yeah, I have a class, and now here's a stylistic choice that I actually, thinking about it again, I probably wouldn't do this next time, but I've included all types of things in here. So first of all, I'm sorting by x coordinate, and then I'm sorting by type. So this is important. And then I've made the choice to include y1 and y2, which are kind of, so I didn't need to include this in here. So what I could have done is kept an external vector of y1 and y2 and just use the index to retrieve this. So I don't need this stored in the class. I could have stored it somewhere else, but both work. And you'll see what I did with this y1 and y2. So anyways, I process each line. So the way lines are given is you get the coordinates of both points, x1, y1, x2, y2. So if x1 is equal to x2, then of course it's a vertical line like this. I give it this event. So the x1, x2, it doesn't matter. It's a vertical type. And then the y1 and y2, I give the smaller one first. So this is important because maybe the line is given to you upside down. And this needs to be done this way so that when I query the ordered sets, it works out correctly. And then I give it the index here. And otherwise, I have to create a start and end event for a horizontal line. Excuse me. All right. So sort, maintain the answer, and now I have this oset. So this oset will store the y coordinates of active lines. And the way my oset works is it contains pairs. So the pair will be the y coordinate, comma, the index. So I maintain the index just to make sure that maybe I don't have duplicates. Although now that I think about it, duplicates will never occur because the horizontal lines will never overlap each other or touch each other at a single point. So all the horizontal lines are disjoint. So actually, we didn't need to worry about duplicates, so I didn't need to use a pair here. Okay. Anyways, we did throw events. If it's a start, we insert it. If it's an end, we erase it from the ordered set. And now we update the answer basically. So we take the difference of the order of the keys, which are respectively where the line ends, where the vertical line ends, like one past it, and where it begins. So this is just the update on seeing a vertical line, and then that's it. Okay. Any questions? Cool. Okay. Let's move along. Oh yeah. This is an interesting problem. Okay. So you're given endpoints in the plane. Print out the smallest distance between any pair of points. So this is sort of like just in terms of time complexity, like the perfect example of where you're reducing a linear factor to a log factor. Because normally, of course, you would just loop over all pairs, but that's not good enough considering n. So now we need to reduce my linear factor to a log factor.
So for this one, it's probably a good idea to give the first hint slide at least, because it's
Okay.
kind of non-intuitive.
It is very much non-intuitive. I remember. So I already knew the solution for this like a year or two ago, and Joe told me this problem the other day, and I just like didn't know how to do it. So yeah. So you sort points lexicographically. So one common thing that we do is we add a comparator for points, so that we can sort them just normally. So yeah, so we're doing a sweep line, of course. We're going from left to right. And the important thing is we maintain the shortest distance we've seen between any 2 points so far. So now, so yeah, the point is that the active points, will be points which are at most d distance away on the x-axis from the next point. So if this is the shortest distance we've seen so far, d, then we don't want to include any points that are more than d away from this point on the x-axis. So now the idea is that we want to do an update on the shortest distance using this point and the current active set. So one thing that we want to do when we see a point is we want to make sure we find the shortest distance, or rather, we want to see if there's a distance less than d between this point and any point we've seen before. So given this set of on points, how could I find points that are potentially less than distance d away from this point? So if you feel like what you might say is too inefficient, maybe it's not. So just suggest it.
So we want to find. So we can use the order. I think we can use the order set again and find all the sets that are in D range, and see that if we need to update those points is like those points distance to our current
Yeah.
point.
Yeah, so actually you don't need an ordered set, but a set actually, yeah, just a set is fine. So Rajat is suggesting this. So if that set, so the set of order points was ordered by y coordinate, you could check through all of them and check the y coordinates which are within D of the new point. So that's basically what we do. So obviously to be within distance D, you have to be within this sort of semicircle. So obviously the semicircle is contained within this rectangle. So we just check everything that's in this rectangle. So to check with just a set, you would do a lower bound on the y coordinate. So like this point minus d. So you check the lower bound and you keep incrementing this pointer in the set until you go beyond this point. This point's y coordinate plus d. Okay. So the question is, what if there's too many things inside here? So can we guarantee that there's not that many things inside of here?
Like if it was, then D would be really small before. Like I don't think
Exactly.
D
Yeah.
will increase. D will never increase over time.
Yeah, exactly. So D is monotonically decreasing. So actually, this is the worst case. Everything will have to be D distance apart. So that means that if we have a rectangle that's D by 2D in dimension or in size, I guess, this is the worst case. So there's only 6 points in here in the worst case, which means we can check kind of in O1 everything that we want to. So actually, it is efficient enough. So then the solution becomes yeah, n log n, right? Yeah. So one thing to note is that the end events are not the same as before. So because you don't know the d at which you will remove a point a priori, so you can't create end events until you're ready. So what you have to do is every time you process a point, let's say you updated the d or maybe you didn't, but basically you have to check the things with the lowest x coordinate, and if it's at distance like and you have to actually it's more like if you're going to see this point next, for example, then you should see okay, well this point is greater than distance d away from this on the x-axis, so now I should get rid of this. And when the smallest x coordinate has been removed that you are going to remove, then you can continue and finally process the next point. So it's slightly different in terms of flavor of sweep line, but it's pretty similar. Okay. Oh, there's code. Great. Okay, yeah, Joe, can you explain this code?
Yeah. Okay. So at the top, I just have like a function to square a number and a function for given two indices. It gives you the distance between those 2 points. Okay, so then what we do is we read in all the points, sort them. The default sorting order for pairs is going to be the lexicographical order that we want. So that's nice. And then we initialize D to be the distance between the first 2 points. And we initialize the set to, basically the way we store our set is as y coordinate comma index of the point. So that way we can recover the index of the point and do stuff with that when we have to like modify the set. But we want it sorted by y coordinate so we can do that upper bound, basically. Yeah, so we're going to initially just put the first 2 points into the set. And we're going to store a pointer to the earliest thing that is in the set. So the first thing in the set right now is index 0. So we set IND to be 0. Okay. So then we're going to loop through all the rest of the points, starting with the third point at index 2. And this while loop is where we take things out of the set. So basically, while the earliest point in the set is too far away in terms of x-coordinate, we're going to take it out of the set and increment IND. So that way we're making sure that that everything from IND up to I is within D of the x-coordinate. So this
So that
set
was
is
sorry. Yeah, that's like removing things that are not supposed to be inside this radius.
that are not in the red area.
Yeah.
Yeah. So then what we're going to do is basically we're going to keep taking upper bounds until we get out of the blue box. So the first one we do is LST, which is sort of what we want to do is we want to get the point that we find the upper bound of. So basically we want a point that has that's going to be strictly bigger than this value here, this floor of the y minus d. So if you look at what we do with LST in the first iteration of the while loop, we take the upper bound of that point. So we find the first point in the set that's greater than that, which essentially gives you the lowest point in the red area.
So that would maybe find
yeah.
like this.
Yeah. And then, so if we have gone past the end of the set, or if the y coordinate is too big, we're going to break out of this loop. Otherwise, we update D, and we're going to set LST to be this iterator, or the point pointed to by this iterator. So that way we can take the upper bound of that point to get the next one.
Yeah.
And then at the end, you want to make sure you add the point itself into your set.
Yeah, cool. So just a style thing, you can also write these sort of loops as like for loops, which can be kind of nice.
Yeah.
So it would look pretty much identical to a for loop where this is your I, this is your check. Yeah. Okay. Any questions on this code or the solution itself?
What's the set precision thing at the bottom?
So this is how many decimal points of precision count will print with. So there's another way that I also do this. It's just a command count.precision something, and then you on the next line you will count out whatever you want. I prefer that because you don't have to keep spamming set precision.
Cool, gotcha.
Okay. Make sense otherwise?
Yeah.
Cool. Okay. Let's keep going. Oh yeah, so this problem was on the NAQ just like a week or two ago. Actually I don't know how long it was. Anyways, so yeah,
I think you guys were there, right?
Oh.
I think so.
Yeah. This was like B, one of them.
B, yeah.
B, yeah. Okay, so actually, for the sake of the recording, I will still explain the problem. So yeah, Alice has n circles that she wants to draw in a particular order, and when she draws a circle, it'll cover any parts of previous circles that she's already drawn. So given this setup, calculate the sum of perimeters of circles that will remain when she's done drawing. Just for the sake of a picture. If you have a circle like this, and she draws next a circle like this, then this would be erased. And then the answer would be the sum of the arc lengths here. Okay. So I don't know how much you guys remember about this problem, but feel free to say as much as you know.
So one thing you can assume you have is you have a function that can give you the intersection points of two circles, because that's kind of a separate thing, and that was tripping us up for a while when we were doing this.
Yes. Yeah, so Jason's suggesting that we can find the events that we want to process using the intersection function. But let's try to make this a little more concrete. So how do I actually want to like process stuff? Like, how am I going to set up my sweep line? So one thing that helps is if we formulate the problem like this. Given the ith circle, we want to compute how much of the ith circle will be present or like not erased after we've drawn everything that comes after the ith circle. So in that sense, we can kind of process each circle individually.
Oh, so you're saying like a circle will be made up by like events, right? Events where like these start and ends, or like from like you can have a lot of circles intersecting, but made up by these like sections of a perimeter. Right?
Yeah. Oh, sorry. But yeah. So like, well, let me do a new one. What? Okay. Yeah. So yeah, maybe I had some circle that I drew. This is the ith circle, but like some of it got erased. So as a result, all I have is this. So like I would want to calculate somehow what these regions are. And once I know the regions, it's actually really not so hard to figure out the remaining perimeter. So yeah, this is kind of two parts. So how do I figure out these regions? And then from there, how do I, of course, figure out the actual perimeter that's remaining?
You just go around. I don't know, go around the circle.
Well, yes, it's a sweep line.
Yeah.
So there's a couple of non-trivial things that are happening. So one thing to consider is like, let's say one circle is intersecting like this. Okay, that's not a circle. That's better. And another one is like this, and another one is like this, and there's yet again another one like that. So like now I have all these like random start and end events. So it's a little bit weird, but I guess the somewhat obvious thing to note is that we only want to count the regions where there are no intersections. Yeah. So I guess kind of the problem is not so hard once we formulate all this, but the implementation can be a little bit weird. So I have some code here. The reason it's not in a slide is because it's kind of long.
Sure.
So okay, so let's just go through it piece by piece. So in our geometry template, we formulate circles like this. Or well, first of all, we formulate points like this. Also, is this visible? Like, is this readable at this size?
Yeah, it's good for me.
Cool. Actually, I'll make it a little bit bigger because the recording isn't so good with
Yeah, they
quality.
probably like compress it, so.
Sorry?
It probably gets compressed, so it's like the quality goes down.
Yeah, I don't think we have a choice in the matter. So, it's kind of like free storage. So, okay, well, this is probably good enough. Anyways, so yeah, we store points as complex numbers. Where the a and b and the complex number is LD. Excuse me. And circles are so you have those. You store the point, which is the center, and you store the radius. Okay. This is a nice macro for checking if a number is basically 0 within epsilon precision. And you'll notice here we've chosen to make epsilon 1e minus 12. This is a curious choice. This is pretty small. But it turns out we were getting WA without this. And I wish I could comment more on about this, but it's a little bit mysterious to me as well. And when we say I here, it's a little bit confusing, but we mean the complex number I. Okay. All right. So this is a black box function for intersection of two circles. It gives us a vector of points of all the intersections. So it helps to recall that circles can intersect in 0 points. They could intersect at exactly 1 point, like that, or they could intersect at 2 points. So yeah, it gives us a vector of points, and it may either have 0, 1, or 2 points. Okay. And we don't really care about what's going on inside here. As long as the implementation is correct, it's fine. But if you know the story, we had like 2 or 3 incorrect implementations that we went through before we finally got AC. Okay. All right. So one of the annoying constraints on this problem is that you can have duplicate circles. Note that if you have a duplicate circle, only the last time you draw the circle kind of matters. And also that means that anytime there's a duplicate, you can kind of, oh wait, sorry, only the last time it's drawn matters. Ooh. Actually, this is, okay, so I've modified this in a slightly problematic way. Okay, but let's not worry too much about that. Basically, the way I modified this code after we got AC is that I made it so that things are not inserted if they've already been seen, but it should be backwards. So like things that have already been seen should only be inserted on the last time that they're seen. But sans that, I don't think I've modified this in any other way. That should be an issue. Okay. Yeah, okay, so we just read in the circles and put them in, and the way I'm doing it, if you've already seen it, they're not inserted. Okay. So again, we're doing types. So we have open and closed events. So the way this works is like, so we start from theta equals 0, and open means that we are starting to intersect another circle, and closed means we're not. So this would be a start event. And this would be an end event. Okay. So yeah, we have open and close, and then the events themselves, they are at some angle, they have a type, and they have an index. And the index is important. Okay. Yeah, so we can pretty much start the sweep line at this point. Or no, we can start setting up the sweep line. Okay, so we're gonna find that how much of the ith circle is remaining after everything after it has been drawn. Okay, so we keep one flag for if it has been completely covered. So like it would be completely covered if this is the ith circle, and then some circle after looks like this. So of course there's no intersection here, but this circle is completely erased, so the answer is 0 for the circle. Okay, so yeah, so let's look at every circle that comes after the ith circle. So D here is going to be the distance between their centers. So recall that because we're using complex numbers, to get the distance between 2 points, we can just take their difference and then take their magnitude. So that'll be the distance. So let's find the distance between 2 circles. And now this check, let's forget the epsilon for a second. It's just checking, basically, if the jth circle is so big that it's encapsulating the inner circle. So let's make this drawing a little bit more clear. So let's say we have like a somewhat small circle and we have a really big circle. So this is D. And now we just have to check the relative radii. So we know where this center is. So if this R was like less than sort of this distance, then we know that this inner circle is contained. And that's basically what's going on in this check, but just in a nice way. Okay. Now this epsilon. So you notice we've added a plus epsilon to this big radius. So what this accounts for is, let's say that the circles do actually intersect, but only at a single point. we don't want to erroneously like ignore this. So what we do is we just say, okay, well, actually, this circle is just a little bit bigger than what you expected, and therefore it get count as being inside. So this kind of epsilon trick is helpful in this case. And the value of this epsilon doesn't matter as long as it's pretty small. So 1e minus 9 is okay for this. Okay. I should go a little bit faster considering the time. Okay. So let's get the list of all the intersections. And if we have less than 2 intersections between 2 circles, then we're going to ignore it. Because if it doesn't intersect, then obviously nothing's happening. If it intersects at a single point, then our ith circle is not really losing any area. It's losing an infinitesimal amount, so we can ignore that too. So only if there's 2 intersections do we actually want to do some sweep line business on this. So now, yet another Aggie. So one important thing is, how do I know which one is the start and which one is the end? So obviously if I draw a picture, it's pretty obvious, right? Like clearly here I start the intersection, here I end the intersection. But if I just give you 2 arbitrary intersection points, well, which one is the start, which one's the end? It's actually not clear, right? So what we do is we pick 1 point arbitrarily, and we increment the angle by just a tiny bit, and we see, is this point inside of the other circle? And if the answer is yes, then this circle must have been like this, and therefore you're starting from this point. And if it's not inside of the circle, then we swap the 2 points. So this is a very clean trick for figuring out which one is first. And now we compute the start angle. So we have an F mod L because we're doing some, I'm not going to get into the details, but we're doing a little bit of arithmetic and we want to mod it by 2 pi at the end. And we compute the end angle similarly, and then we add these events. Okay. So if the circle has been covered, then just continue. Now, sort the events. And so we actually got TLE when we use this set to show which indices are currently on. So we switched to a vector of just saying which things are on, and also keeping a count. Because the only thing that matters is if the count is 0 or not. And this data is storing the last time that we were actually including that interval. So let's go back to this picture. So in this picture, when we start this interval here, that means that we're not counting the area anymore. So I want to add this parameter to my answer. So in order to do that, I need to know where I started the interval from, and that will be what data is. Okay. So now this is the first loop where I do the initial processing just to see what's on at the beginning. So I go through every event. If it's open, I set it to, sorry. If it's open, then I will set this index to be on. This interval is on. And if it was off before, then I increment the count. So this is basically just keeping track of a set size. And then same thing here for off. So at the end of this, I know exactly which intervals are currently on at theta equals 0, and I know how many of them there are. Now I do the actual processing. So for each event, if it's open, we have to do something special if it's the only thing that will be open now. So let's say there's one interval here that will be opening here. So like I just mentioned, since this is the only thing that's open now, so let's say there's just a single circle here. Since it's opening now and there was nothing else before it, I need to add this parameter to the answer. So what I do is I take the current angle minus the last data, and I multiply by the radius, and that's how much perimeter goes onto my answer. And then otherwise, I just do the set manipulation, which is precisely the same as before. And similarly, I might need to update data. So like here, it's closing. So here, I will update data. So again, when I see this circle here intersecting, I know that this will be E dot A, the events angle, and I'll again add this answer, this perimeter to the answer. And then the final thing is that let's say at theta equals 0, I am. I don't know. Sorry, that was bad. Yeah, let's say at data equals 0, there's nothing currently active. So I need to make sure to add this perimeter as well, because I was normally only adding the perimeter when I saw this. So that's what's happening here. If nothing is currently active at the end of my sweep line, I need to add this to my answer. Okay, and that's it. So I'm sorry, that was a pretty rushed and like lengthy explanation. But if you have any questions, go ahead. I'll try to answer. Okay, cool. Cool. Yeah. This is actually a very nice sweep line problem. Because it's kind of a nice abstraction where you can do this independently for every circle. And it's kind of a standard circular sweep line problem. Very good reductions in here.
Oh, at least I actually have one question.
Yeah.
Did you sort the how did you choose like the way we're processing the circles, or was that arbitrary?
So it doesn't matter. Actually, no, it does matter. One thing. So of course, we're gonna start from data equals 0, and go this way. You can go the other way too. That's just as good. But you might have to do some calculations differently. You could also start from data equals whatever, like pi over 2. And again, some calculations be done differently, but the natural choice is to go like this. One thing is that the order of the events, if there's a tie. So if you might have noticed, we have a minus epsilon for start angles and a plus epsilon for end angles. So the reason for this is that, let's use yet another Aggie. So let's say that we have an interval like this and another interval like this. And let's say that we introduce some accidental epsilon distance in between here, like some miscalculation. So we don't want to add like this epsilon area, or rather not epsilon. We don't know how big this area is, because if the radius is really big, then like, even though the angle is small, like if the radius was like 1e18, then like, oh my God, like we just added a bunch of area. So yeah, what we do is we kind of like force it to overlap by instead making it look like this. Right? Because we added epsilon to the end like this, and we subtracted epsilon from the start. So in this case, they will like definitely overlap. Yeah. And the epsilon was very tiny. It was 1e minus 12. So we were very cautious. And I think, yeah, we WA'd with like 1e minus 10, I think. So we made minus 12 and we got AC.
Gotcha. Okay.
Yeah. Okay, cool. If that's it, yeah, thank you guys for coming. And yeah, see you next time.